Do you want to see something really cool? Of course. Turn off the lights. Industrial strength night vision goggles.
Holy Santa Claus. Can you imagine if we had these when we were 12?
Even better. We got them when we're 40.
You know what's amazing? They're not that noticeable on your face.
Right?
Yeah.
Turn the music up in the headphones. Tim, you can go and brush your shoulder.
As you probably already know, our project is on night vision. In this presentation, we will discuss the background and evolution of night vision, the types of night vision, and the quantum mechanics of night vision. Welcome to Mr. Burson's history class, where we talk about night vision and night vision only.
Mr. Burson, I have a question.
Yes, Mr. Gollum?
When were night vision devices first introduced?
Good question. They were first introduced in World War I. Night vision devices were originally the military's answer to night combat. In World War I, large searchlights were used at night. This would illuminate both enemies and allies, so they needed something to stay covert, thus the idea of night vision.
How did the idea change from World War I to World War II?
By World War II, the first crude night vision devices were developed, using lamps with filters that only passed infrared light. Because infrared light is not visible to the human eye, soldiers could easily carry and use image converter tubes that changed the infrared light into visible spectrum and allowed only the users to see its desired areas. These devices were active, which we will explain later. By the Vietnam War, they improved to passive devices, which we will also talk about later.
In the future, night vision will evolve and become a tool that is used more frequently and be more effective. The military is starting to use night vision in a more tactical way. Most landmine detectors consist of a variety of sensors that look for abnormalities in the area. Thermal imaging is often used because there are detectable differences in how explosive devices in the surrounding soil absorb and release heat. Night vision devices will soon allow us to see the universe in ways we have never seen. This is because dust clouds and other debris block our view of the nebula. With infrared, we can see stars and planets beyond our capabilities today. For example, this picture is taken in both visible and infrared light. The picture taken in visible light on the left contains a lot of information about the nebula. However, in the infrared picture on the right, you will see many stars that do not appear in the visible light picture.
There are two classifications of infrared night vision goggles, passive and active. Passive night vision goggles are capable of catching any light within a close range. The goggles then amplify this light many times over by the usage of image intensifiers. It is similar to adjusting the contrast of a picture. The other classification of night vision is active night vision goggles. They project a near-infrared light source. The optics in the active night vision camera are sensitive to this spectrum, but they are just out of the visual range, so you cannot see it. There are three different types of night vision devices, all which depend on infrared light in different ways. All people and things give off far infrared light. Far meaning infrared light near the microwave part of the spectrum. The detector elements of the goggle create a very detailed temperature pattern called a thermogram. Based on the temperature differences in the scene, hotter objects appear brighter than cooler objects. Thermal imaging is a passive type of night vision, meaning it comes from the natural light that was not created. Thermal is different from the other two types of night vision because, in general, thermal energy is emitted by an object, whereas in the other types, infrared light is reflected off of the object. The thermogram created by the detector elements is translated into electric impulses. The electric impulses then translate information into data for the display. The signal processing unit sends the information to the display where it appears as various colors, depending on the intensity of the infrared emission. Low-light night vision goggles require that there is some light in the area. It acts as a light amplifier. It works by intensifying the light signals, like a speaker that amplifies sound when you turn up the volume. The goggles take ultraviolet, visible, and near-infrared light and use electronics to amplify the signals and create a visible picture. This type of imaging can either be active or passive. It does not need to create and project light, but some types do. Near-infrared imaging requires two parts, an infrared emitter and an infrared detector. The emitter sends out infrared light, and then the detector records the picture. It is like a photographic flash. When you take a picture, the flash lights up the object and makes the image brighter in the photograph. Only in this case, the flash is infrared light instead of visible light. This technology is useful in cases such as security cameras. This is an active type of imaging because the infrared light needs to be projected in order for it to work.
You ready? Let's go!
Well, hello there, children. You came just in time. I'm about to teach everyone about photoelectric effect and how it plays a role in night vision devices.
Excuse me, when was the photoelectric effect first discovered?
Night vision goggles depend on the photoelectric effect, which was explained by Albert Einstein in 1905 using quantum theory.
How does it work?
Well, to look at it at the atomic level, Einstein explained how light has a particle and wave duality. Basically, when a polished plate is exposed to electromagnetic radiation, the photons that hit the plate act as a particle and knock off electrons. These electrons are referred to as photoelectrons. These electrons are only emitted if the frequency of the light exceeds the threshold value. The magnitude of the emitted current of the electrons depends on the intensity of the light source, and the kinetic energy depends on the frequency of the light source. Please watch this short video on the photoelectric effect. Hopefully it will help broaden your knowledge on this phenomenon.
The photoelectric effect is the ejection of electrons from a surface when light of sufficient frequency shines on it. For example, when red light is directed at a metal surface, no electrons are ejected. However, when blue light, which has a higher frequency, is directed at the metal surface, electrons are ejected and a current flows through the wire as measured by the ammeter.
When blue light shines on the metal surface, electrons are knocked out of the metal. As long as light of sufficient frequency shines on the metal, free electrons are produced and current flows through the tube as measured by an ammeter. The current stops flowing when the light is turned off. When yellow light shines on the metal surface, electrons are knocked out of the metal. As long as light of sufficient frequency shines on the metal, free electrons are produced and a current flows through the tube, as measured by an ammeter. The current stops flowing when the light is turned off.
Welcome back. I hope that video helped improve your knowledge of the photoelectric effect.
How does the photoelectric effect play a role in night vision goggles?
Good question. I was just about to get to that. In night vision goggles, the photoelectric effect is used to amplify individual photons. The photoelectrons are accelerated through several hundred volts to a channel plate containing many holes. These electrons are then accelerated through the photomultiplier, which produces even more electrons by using a high voltage to propel them down a tube. The electrons then strike the phosphor screen, which reacts, creating a pool of light which is visible to the human eye. This allows us to see in the dark and all the fun stuff that we can do with night vision goggles. Current night vision devices consist of 5 main components: a photocathode, a microchannel plate, a phosphor screen, and 2 lenses for collecting, magnifying, and focusing the images. The first lens captures both visible light and infrared radiation. The photons of light hit the photocathode, which absorbs the energy of the photons and emits electrons with the corresponding energy. These electrons then collide with the microchannel plate, which releases thousands of other electrons with the same energy. Secondary emissions occur when the original electrons collide with the side of the walls and excite the atoms. These excited atoms release their own electrons, which repeat the process and go on to excite other atoms. After passing through the microchannel plate, the great number of electrons finally collide with a phosphor screen, placed at the end of the night vision device. The phosphors are energized by the electrons and release photons to create the brightened and magnified image through the last lens on the way to the human eye.
Go, 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 shorty. It's your birthday. We gon' party like it's your birthday.
This is a video of a nighttime raid in the Middle East. As you would expect, night vision is mainly used for military operations. The military uses night vision goggles for flight, security, and also being covert. Night vision has also been introduced to the public, and humans tend to use them for their own entertainment. Because of night vision's success in military flight, civilian pilots and rescue operations who often fly through darkness and bad weather often use night vision. This tool allows medical pilots to spot any patients in the dark, as well as reducing the potential of crashes. This technology has even made its way to luxury automobiles. Companies have started combining technologies to create night vision screens, infrared high beams, and even pedestrian tracking devices. These new enhancements can extend the visibility of drivers at night and during fog and rain to over 300 meters, which is really good considering the normal 50 meters provided by regular headlights. A good example of this is the Mercedes-Benz night vision screens. Please sit back and enjoy the experience of night vision driving.
However, the risk of a serious accident is much greater in twilight and darkness than during the day. The 8-inch display is directly in the driver's line of sight and can be used just as easily as the speedometer and other cockpit instruments. Regular glances at the infrared display image give the driver a quick, long-range view of the road situation.
After watching our video, I hope you learned a lot about night vision. As you can tell, it has a very detailed history and explanation of how it actually works. It is an amazing tool that can grow and evolve in the future to become even more than it is today. I really hope you thoroughly enjoyed our presentation.